So here we have two examples of unit cells. These fall in the family of cubic unit cells. So the angles at the corners are all 90 degrees, and the lengths of the edges are all the same. So we'll call that unit cell length L, right? And we're going to relate, what we're going to be doing in this slide is examining how you analyze and find the length of a side and its relationship to atomic radius, as well as how we count the number of atoms that are in a three-dimensional unit cell. So to start with, in the simple cubic unit cell, what we have is an atom at each corner. So you can imagine that at this corner there would be an entire sphere. Now how much of the atom is actually in the sphere? So if we're looking at the corner, what we find is in thinking about XYZ, right, Cartesian coordinate system, right? How many quadrants are at the top and how many quadrants are at the bottom? And if you count it correctly, you have 8. So if you think about what this sphere represents, it actually, or this portion of sphere represents, each corner is 1/8 of an atom. So the way you get the total number of atoms in a simple unit cell, simple cubic unit cell, is you just say how many atoms are in the corner. So you have 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 atoms. And let me do it like this. 8 corner atoms. I'll just call them CAs, right? Times 1/8 per corner. And so there's a total of 1 atom in the unit cell. Now, if you look at this body-centered cubic cell, what we have, and the color is just to help us see the difference. It's actually the same size as this one. It just looks bigger because we're seeing the whole thing in the image. So in a body-centered cubic cell, it meets the same criteria of edge lengths are the same, and the angles are all 90. But when you're counting atoms, you have a body atom. So this is the body, right? That is, it's in the entirety of the atom is within this unit cell. So it's just times 1. And then you have, again, 8 corners. So this represents 8 corner atoms times 1/8. That gives me a total of 1 atom. Now, what we do to get the total number of atoms in the unit cell is we take and add these two together. And so I have 1 atom for the corner atoms, and then I have plus 1 atom that's in the unit cell. So I have 2 per unit cell. Now we're going to look at what the relationship is between the unit cell length, that's L, and the radius of the atom, which is R. Now, for the simple cubic unit cell, it's pretty easy to see that the span of the unit cell actually goes across, right, 2 radii. Right, this would be half an atom to here. That's 1 radius, and this is the radius from the other side. So L is equal to 2R. So how do you do it, though, when you have something where they're not touching at the sides? And the way you do it is you do the following. You say to yourself, well, I have an atom here in the corner, and I have another atom in the corner here. And you'll notice that if you draw the diagonal across like this, right? And I'm going to draw it sort of erasing this atom here and drawing it sort of two-dimensionally. What you have is basically a square, an atom in the corner, an atom in the middle, and another atom in the corner like that. So that's what this line is tracing across the diagonal on the unit cell. So I'm going to call this value C. Okay. And then I'm going to say that C is equal to 4 times the radius. Now, the question is, how does C relate to the unit cell length? And now you have to sort of imagine, many of you haven't seen this before, but this length is L, and this length is L. And most of you know Pythagoras' theorem. Pythagoras' theorem says if you have a square and you draw a line like this, that the diagonal, or you could really just draw a right triangle, but it's easier to see it if you draw a square in a lot of ways. In this particular example, you can say, well, that L, right, squared, or sorry, C squared, is equal to A squared. I'm going to call this A because I'm so close to the bottom of the screen, and I'll call this B, is A squared plus B squared. And that's Pythagoras' theorem in 2 dimensions. In 3 dimensions, it ends up being that A squared, or sorry, C squared, will be equal to A squared plus B squared plus C squared. So we have, in terms of sides, right, can be L is A, L is B, and this L is C. So what we end up getting is that C squared, that is the diagonal, right, is equal to 3A squared, because all I have to do is substitute it, or sorry, 3L squared, because all I have to do is substitute in for A, B, and C the value for L, so then I end up getting 3L squared. Okay, so if I want to know the value for L, then what I do is I can substitute in for C 4R. So now I have 4R squared is equal to 3L squared, like that. And I'm going to take the square root of both sides. So that becomes 4R is equal to the square root of 3 times L. So L ends up being equal to the square 4R over the square root of 3, like that. So this would be true for any body-centered cubic. And if you didn't like the way I did this to get to this equation, it's not necessarily important to know how I get there, but if you want to see a different way to do it, you'll notice the book uses a slightly different method. They use just 3 sides. They don't use the Pythagoras theorem in 3 dimensions. So there's another way in the book they show how this relation works out. So anyways, this is the kind of stuff that you need to do in order to find the value for L and the number of atoms per unit cell. And it turns out these 2 values will be very important in determining or calculating properties of materials based on their unit cell and the dimensions of their unit cell. So there are 3 kinds of cubic unit cells that we cover in this chapter. We've looked at the simple cubic unit cell and the bodied-centered unit cell. We're going to look at face-centered here shortly, but when we get to face-centered, what you'll see is there are 4 atoms per unit cell, and this is just a table from your book. The structures, right, for simple are what you're familiar with in bodied-centered, but in a face-centered unit cell, what happens is there's no body atom in the middle, but instead at the face of each of the, inside the face of each of the faces of the cube, we have half an atom inside and half an atom outside the unit cell. So this is why they call it face-centered, is you have this square, right, for the unit cell, and within the middle of those atoms you have another atom that's sort of protruding from that face. Now when you look at the coordination numbers, you can see that the coordination numbers for this bodied center are 8, because you can see there's 8 atoms at the corners and those are the ones touching. Turns out the coordination number for simple cubic is 6, and that's because when you pack the next unit cell adjacent to it, for example, let's say next to this guy, so we're going to go like this, right? That if you think about how many atoms this corner atom is in contact with, well, it's in contact with 1, 2, 3, and then 4, and then 1 in front, 5, and then 1 from the bottom, 6. So there's a total of 6 atoms in the unit cell. The coordination number, though, for a face-centered cubic unit cell, which you can't quite tell from here, so we'll look at that later, is actually 12. It's quite high. In terms of edge length, right, the unit cell length, in terms of the radius, we've already shown that the simple cubic is 2r, bodied centered is 4r over the square root of 3, and face-centered is 2 square root of 2 times r. So make sure when you do this formula that this r value, its equation should maybe best be 2r times the square root of 2, and then you don't get confused whether or not the r is inside the radical or outside. Now, in terms of packing efficiency, one of the things that we talked about before, actually in the previous segment, we talked about, packing efficiency here, right? The packing efficiency is essentially the percentage of the volume of the unit cell that is occupied by atoms. And we also said that as the coordination number goes up, the packing efficiency goes up. So you can see that here, when your coordination number is 12, your packing efficiency is 74%. And you can also see that in this picture, like each one of these atoms makes contact with a lot more atoms than this does. So for example, this atom in the face here makes contact with 1, 2, 3, 4, 5, 6, the yellows, 7, 8, and then there's another layer on top which would give us the 12. Okay, so 3 layers of 4 is one way to look at it. So I'm going to show you how you calculate the packing efficiency, and we're going to do it on a 2-dimensional crystal lattice. And the first things that you're going to have to do is, first of all, look at the definition of packing efficiency. It's the occupied area divided by total area. What we need to do first is figure out what our unit cell is, because once we know the unit cell, we can calculate the area of the unit cell, and we're going to do that in relationship to the radius of the atoms. So if I'm looking at this as my crystal lattice, what point do I pick, right, to start? And it turns out there's a couple of places you could start. You could start here, for example, or you could start here. But all you do is you draw a line. Let's say we start here, and then you just draw it so that you can encompass a pattern that can be repeatable. So if I had started, for example, up here, I could have done the same thing. This was actually a little more cubic than the one I just drew, but you could start up there and you can get something like that. So let's analyze this first one. I'm going to put a dot in the middle of each, right? Those are going to be lattice points in essence at some point, but just draw that. And what we'll notice is if I take this and I just transpose it one set of atoms to the right, I'll get the exact same pattern. So this is a good representation of the unit cell. Now, to calculate the total area, you just need to know the area inside this unit cell. And let's call this the cell length, these two values. It's supposed to be square, so let's just say that this is the cell lengths. Well, how is that related to the radius? Well, like we did for the bodied centered, right? Just draw a diagonal between the corners of your unit cell. And what we find is that 4 radii, right, that's what this is, squared. And we're using Pythagoras' theorem here. So this is the hypotenuse, right, is equal to L squared plus L squared. So it's a squared plus b squared equals c squared. Well, c is my 4r. Now, in order to calculate the area, what I actually need is just to isolate L squared. So I'll end up with 4r squared is equal to 2L squared. And all I need to do is divide through by 2. So that actually is the equation for the area of the unit cell, since this is L squared. Now in cubic unit cells, what you normally do is you take the cube root and then or the square root of it to get L squared, and because it's in 3 dimensions, it's a cube, you have to cube that value, okay? But it works well for us in this example that the volume just comes out to be L squared. So my total area, my total area is just L squared, which is equal to 4R squared over 2. Now the question is, what area is occupied by circles, right? Well, you can kind of see there's a whole circle here, and these each represent quarters of a circle, and there's 4 corners on a square, so there's actually 2 circles per unit cell. So I have 2, and we'll call them atoms, not really atoms, but we'll call them 2 atoms per unit cell. Now, what I need to do next is to figure out the area per atom. Well, these are circles, right? And so if we know the radius of the atom, each one of these has an area of equal to pi r squared. So this is my area per atom. So 2 atoms per unit cell times my area per atom, which is pi r squared per atom. And that gives me the area occupied, right, by atoms in my unit cell. Okay, so let's just rewrite this. I have 2 pi r squared. That's my occupied area. And then I have 4 r squared over 2. So I'm just going to do the algebra and expand that out. 2 pi r squared is equal to 16 r squared. You notice my r squareds cancel, divided by 2, like that. So what I'm going to end up doing is simplifying. I have 16 over 2, so that's 8, right? So 1 over 8 is a quarter pi times 100. I should have been, this whole time I should have been having the 100 in here, right? The 100 should be here. Times 100%. And we'll go ahead and calculate that. So 3.14159, that's pi, divided by 4 times 100. And so the packing efficiency is 78% for my hypothetical 2-dimensional unit cell. But that's how it's done. You basically calculate the occupied area, divide by the total area, and you end up getting the percent of occupied space, and that's my packing efficiency. So as an example, I'll do the packing efficiency for a simple unit cell, cubic unit cell, and we'll do the calculations based on this diagram that's shown over here. The cell length is L, and then the value for L is actually equal to 2 times the radius. So if I want to calculate the packing efficiency for a cubic cell, simple cubic cell, the occupied volume is the volume of a sphere. So for a sphere, V is equal to 4/3 pi r cubed, like that. And then the volume of the unit cell in terms of R, right? Volume is length times width times height, or L cubed, which is equal to, so this is the volume occupied, and the volume of the cell is equal to 2r cubed. So to get the packing efficiency, the occupied volume is 4/3 pi r cubed times the number of atoms in the unit cell. So if you remember, there's one atom in the unit cell. This is 1/8. Each corner represents an eighth. So I take 8 times an eighth. That gives me 1. So I don't need to, I can go like this, times 1 atom. And then I divide that by the total volume, which is equal to 2r cubed times 100%. I'll simplify that. Might be easier just to show it like this. And then the volume of the unit cell becomes 2, 4, 8, right? So 8r cubed. And then the r's will cancel. And then I can just do the calculation quickly. So I'll take 4 divided by 3 times 3.14159, and then divided by 8, and then times 100. So my packing efficiency is about 52.4%. If we go back and look at the table that I showed you before with the unit cell lengths on it, right? That's where this number comes from. And each of those packing efficiencies can be calculated using the sort of the same routine of calculating the volume occupied by spheres divided by the total volume of the unit cell, and then times 100. This diagram shows a three-dimensional representation of a face-centered cubic unit cell. And in the face-centered, I showed you earlier, there's one atom within the face of the unit cell. Now, if you'll look at this closely, you'll see that half of the atom is inside one unit cell, whereas the other half is sitting into the adjacent unit cell. So what we need to show is what I need to show you is how to calculate the number of atoms that you would find in this unit cell. If you take the corners, we know that we have 8 corners, and each one of those occupies or is occupied by 1/8 of an atom, provided that there are unit cells in each corner, right, or atoms in each corner of the unit cell. And so that gives us 1 atom. But then what to do with the faces, right? So if you look at the cube, what you'll understand, or just even if you have a dice sitting around the house, you can pick it up and look at it. There's 6 sides to the dice. And I think most people know this because when you throw dice in a game, for example, you have the numbers 1 through 6 on them. So there are 6 sides to a cube, and each side has half an atom in it. So for the face set, all right, for the face atoms, we have 6 faces times 1/2 atom per face, which is a total of 3 atoms. And so what we find in the face-centered cubic unit cell, we have a total of 4 atoms. And the face-centered cubic unit cell actually represents the most dense or the highest packing efficiency of the simple cubic unit cells that we're looking at. The other thing to make note of is the edge length of a unit cell, again, which we call L, is related to the diagonal, right, across the face. Because remember what we do when we're trying to figure out the relationship between L and R. We look at the diagonal that goes across where the atoms are touching. So I have one radius here, I have another radius here, then a half and a radius and another radius. So 4r in this case is equal to the diagonal length. And if we're using Pythagorean theorem, again, we find is that's equal to L squared and plus L squared, like that. So what we can do then is say 4r squared is equal to 2l squared. Oh, sorry, parentheses like this. And then I'm going to divide through and solve it for L. And so L squared is equal to 4r squared over 2. And then I'll take the square root of both sides, which gives me L is equal to 4r divided by the square root of 2, which if you remember from your math classes, that's 2 times the square root of 2 times r. Now if we go back to that table, right, 2 square root of 2 is given here as the edge length because of the way we derived, again, across the diagonal that touches atoms, or where atoms are continuously touching across the diagonal. So here's an example problem, edge length and atomic radius relationships. It says a bodied centered unit cell has a cubic unit cell has an edge length of 588 picometers. What is the radius of the atoms composing the unit cell? So there's a couple of things we have to pay attention to here. First of all, we need to know what kind of unit cell we're dealing with. Right, so this is a bodied centered cubic unit cell, and it has an edge length of 588 picometers. So in solving this kind of problem, what we need to do is we need to go find the right equation or rederive the equation based on our knowledge of the unit cell. Simplest thing to do is go look at bodied centered cubic unit cells in this table. I would keep this handy if I were you. So bodied centered cubic, okay, unit cell, 4r over the square root of 3 is the edge length. So L is 4r over the square root of 3. And what we're being given is we're given the edge length, right? That's L. And then we're being asked what is the radius of the atoms. So we'll solve the equation for r. Like that. And then simply insert 588 picometers for this length. That gives me 254.6 picometers. With three significant figures, that rounds to 255 picometers. So this is the correct answer. No doubt these other answers are calculated using the wrong unit cell, right? So one of the things you need to be aware of as you do these problems is have these equations handy, and then make sure you understand that you need to know the unit cell in order to use the correct equation. Here's another variation of that kind of question. It says, an atom has a radius of 138 picometers and crystallizes into a bodied centered cubic unit cell. What is the volume of the unit cell in centimeters cubed? So again, what we need to pay attention to is the type of unit cell and the information we're given. Again, we're looking for bodied centered cubic, right? So the same one here. So L is equal to 4 r over the square root of 3. Now, what we're being asked to do is actually find the volume of the unit cell, right? And we need to find it in centimeters cubed. So what that means is I'm going to have to take this radius and convert it into centimeters before I do my calculation, or I can calculate the volumes in picometers cubed and then convert that over. So I'm going to go ahead and calculate R in centimeters. So R in units of centimeters. So that'll be 138 picometers. So what I'm going to do is simply go times 10 to the minus 12 meters. And then I know for every meter, you could do this two ways. I could say 1 centimeter is 10 to the minus 2 meters, or I could say 100 centimeters is a meter. Either definition either conversion works. And so this gives me, I'm just going to do the exponent math here, 138 times 10 to the minus 10 meters, centimeters, excuse me. So I can calculate my edge length. Times 138 times 10 to the minus 10 centimeters. That gives me 3.1870 times 10 to the minus 8 centimeters, like that. And then to calculate the volume, this is going to be L cubed. So that ends up being 3.1870 times 10 to the minus 8th centimeters cubed. Pull up my calculator, and then all I need to do is raise it to the third power. And I get 3.2, and I have, let's see, 3 significance figures, so 3.24 times 10 to the minus 23rd. So there's the volume of the unit cell. Just a couple of interesting notes, right? In terms of Avogadro's number, right, 10 to the 23rd, see how these numbers sort of match with each other in terms of scale or dimension. So that's why you can sort of guess that this is probably about the right value for that calculation.